Okay, so let me then start. I think in the last class I ended with the discussion of the, or at least the mention of this postulate of equal a priori probability. Now, what it said is that if the energy is constant, then all microstates are equally likely. Okay. Now, you had a question, so let me just start with that. You had a question that you were asking what that you had a question, right? How come I have a large number of microstates with E1 bar and so on? In case of thermal equilibrium. Okay. So first, this is clear that if the system is isolated, then all microstates are equally likely, or you have a uniform distribution on the energy interface. Now, when these two systems are in thermal equilibrium, this system may still have energy fluctuations. It is not an isolated system. Just this system. It is not an isolated system, nor is this one. Okay? They may have many different energy values, E1 and E2, such that E1 plus E2 is equal to E. So, the composite system, the entire, the composite system is thermally isolated, but not individually. And therefore, I cannot say that individually in the phase space of just this system, I cannot say that all states are equally likely. In fact, what we would show today in the later part of this lecture is that if it so happens that this first system is much smaller than the larger one, and the composite system is isolated, we will show that the energy distribution of this smaller system is actually a Gaussian with a peak around the value E1 bar that we had computed. Right? And if you remember what was E1 bar, we had said that most of the microstates have got this like energy, but there will be some microstates with other energy. And what we will do is that if N1 V1 they are much smaller than N2 V2, then we will show that for this system, if I look at the energy distribution, I had said that most of the microstates have got the value E1 bar, and indeed it would be E1 bar with a Gaussian, with a small spread around it. The spread will decrease as I keep on increasing n. Is this clear that for this system alone I cannot say that all microstates are equally likely, because it is not an isolated system. So this brings us to the canonical ensemble, the setting of canonical ensemble. But before I go to canonical ensemble, I mean, let me just ask, like, is this thing clear why there is an E1 bar and E2 bar and so on? How does a temperature come out of it as the derivative of the entropy with respect to the energy, and why there are microstates with the energy E1 bar? Most microstates have energy E1 bar, but that does not mean that there are no microstates with energy different from E1 bar and so on. And similarly for the left hand, for the right side also. Acha, before I move to this canonical ensemble, let me do this Gibbs factor that if you remember yesterday we had said that in deriving this result that the entropy of the composite system is a sum of many terms, and there is one term that that dominates, and then I had done some like order of magnitude calculation. This goes as n and n1 and n2. I had told you that this S of E of V, and this is the entropy of this composite system that grows as n. So with the way we have defined it, namely S of V is equal to k log of gamma, where gamma of E was dq dp delta of H minus E, and we had done a calculation for number of microstates or volume of accessible microstates for an ideal gas, and shown that this I think we had computed this sigma. By the way, just a small thing, this gamma of E, this is equal to omega of E times delta. I don't know whether you recall that definition. And then there was sigma of E. So sigma of E was, you consider all microstates with energy smaller than E. And gamma of E was all microstates with energy between E and E plus delta. And then we had said that this gamma of E is nothing but sigma E plus delta minus sigma of E, and then this is the density of states and so on. So you can show that, I mean, you can try this, it is mentioned in Carson Wang, you can do this calculation. I mean, you have to just keep track of all the factors and so on. You can show that S of E, you can define it either as k log of gamma E or k log of sigma E, it does not matter. You will get some corrections that go down with increasing n.
When you say S is k log of gamma E, gamma E is actually the volume of the phase space, right?
Volume of the phase space with energy between E and E plus delta. It is, so what is small omega of E is just number per unit energy interval.
Exactly. So basically it denotes the number of microstates within a energy term. So in the previous calculations when we derived temperature, you said that the total gamma should be gamma 1 of E1 into gamma 2 of E minus E1. Wouldn't it be more logical if we work with small omega? Because that actually denotes the number of states.
Small omega is the number per unit. So that's what I am saying, that for S of E, so there are three possibilities. S, you can define it as k log of gamma E, this is what I was using, or you can say this is k log of sigma E, or you can do it as k log of omega E, like omega E. You can show that these three definitions would give you equivalent results up to some additive factors that that decrease with increasing n. You can do that with whatever so whichever definition you are more comfortable with.
So basically you're saying that while deriving temperature, like the definition of
temperature is defined in terms of S.
Yes.
Now S, for S you can you use either of the, so one of the three definitions, it doesn't matter.
Right.
Yeah, the point is that this delta is a number that's independent of n. So it doesn't really matter whether you do this or this, it is not, this width, whatever imprecision that you are allowing for, that has nothing to do with the system size. While all the other factors, gamma, sigma, small omega, they have to do with the system size, and therefore if the system size is sufficiently large, you can forget about the contribution coming from this imprecision. It's just that. Okay, so in the last class we had derived an expression, not derived, I had told you that this sigma of E for a classical ideal gas is given by some expression, no, the V to the power 3n or something, right? Square root of twice me to the power 3n and so on. So it turns out that if you use that definition and you can take the derivative with respect to E of that expression and get an expression for like omega E and also gamma E and so on. Whichever definition you use, you are not going to get a quantity for, you are not going to get an entropy which is proportional to n. And this has to do with, so in books there is a section called Gibbs paradox. You may read about it. It leads to some inconsistencies. So the way to do it is, at this level it is not clear what one has to do or why one has to do whatever one has decided to do. Apparently what Gibbs had done was, I think he had put it by hand, that you have to just divide everything by 1 by n factorial, and the way that one kinds of argues is that well, the particles are indistinguishable and therefore there are n factorial particles, it does not matter which one you call first particle, second particle, and so on. So that's, at this stage it is done as an ad hoc prescription, just to cure this problem of an entropy that's not extensive, that's not an extensive quantity. But later on, hopefully in the next week when Arnab teaches you quantum statistical mechanics, we will see that this classical gas, it's a limit of a quantum system. You take a quantum system, you go to very high temperature, and whatever you get is your classical system, and you will see why you need high temperature. You need high temperature because what you need is the width of the wave packet associated with individual particles should not overlap. It should be, the separation between the wave packet must be much larger than the interparticle separation, that they don't overlap, and then you can call this as first particle, second particle, and so on. So if you take a quantum gas and take proper limit, classical limit t going to infinity, you will recover this 1 by factorial automatically. That's the ideal Boltzmann gas and so on. But at this stage it is not clear why one has to do, one has to put in that factor, but it has to be there to make the entropy proportional to n. So in that argument that I had used, I had somehow assumed that that factor is already there. And if you read Carson Wang, you will see that in starting from the chapter on canonical ensemble, in all expressions for entropy, for the partition function S and so on, there is this factor n factorial and h to the power 3n put in by hand. Now in the end it will not I mean in calculating the entropy and so on, it will at the stage it is difficult to justify why that factor has to be there. This h to the power 3n, so for teaching purpose you can forget about. You can say that there is some constant, some constant factor which has to have the dimension of Planck's like h bar, but then anyways we will be dealing with log of that, and so this will not matter. Okay, so this was just a comment. And this Gibbs paradox thing, this I am not going to discuss because it's pretty straightforward. I mean, whatever inconsistency that one ends up with, if one takes such a definition of entropy where there is no fact n factorial. Let's are there questions on microcanonical? Otherwise I move to canonical. This thing is clear, right? This so now we consider the situation where, so there are two physical situations that one can think of. Namely, number one is that you have your system. So here what I was doing was, I had said that there are two systems, I brought them in thermal contact with one another. But I did not specify what this system is and what that system is. So very often than not, what you have is your system of interest, and that's in contact with the external environment. Okay, so external means anything external to your system of interest. So that involves our own galaxy and everything that's there. So everything outside my system of interest is external by definition. Otherwise, I would not have called it external. So your system of interest, and then there is this, the whole world outside, external to it. And as you can see, a typical situation is the one in which your system of interest is much smaller than the external world. So what I have to do is that whatever I had done for this setting, I have to just generalize it to the case where I can say that my system of interest is much smaller than the than the other system. So this is my system A and this is my system B, and by definition, since in this system B I have included everything external to it, so the composite system is now isolated because I have included everything. Either it's there or here or there. So the whole thing is thermally isolated, and therefore I can still continue to consider in the same way as I have done there. I can still continue to consider system plus the environment to be isolated. So that's one way of looking at it. The other way is to say that, well, this is my system, whatever be its size, but I could be interested in finding out what is happening in a small in a subsystem, in a small part of it, and which is indeed exchanging energy with the rest of the system, right? So that's also included in that setting. So it's like this is a room, and I could be interested in finding out what's happening in a small volume here, and let's say the room is completely closed, no one is allowed to go out or come in. So that's an isolated system, and I'm interested in what's happening in 1 centimeter cube. So that's one setting, or to put it differently, this is your system of interest. It's in contact with the external world, and at the moment energy is being allowed to exchange between the system and the surrounding. So what I'll do is that I'll go, whatever I did with the entropy and so on, I'll do the same thing. It's the only thing that I have to remember now is why this makes this noise. So the only thing that I have to now implement is the fact that my system of interest is way smaller than the rest of them. So I have to do some Taylor expansion. I am allowed to do some Taylor expansion. Okay, and okay, so now so in dealing with the microcanonical ensemble or that setting, what I was asking was, what is the total number of available phase space or microstates for the entire system, and that I wrote in terms of product of the available gamma space for this one and that one. But now I'm saying that my system of interest is only this one, this one which is here. I don't care about what's happening in the rest of the world. I know that my system plus the external world is going to make up a composite system, but suppose my interest, or I have access to information only, information which is available for this system of interest. So for this system of interest I have a phase space. So this is now the phase space of the system of interest. So this is a system interest, phase space of the system of interest. Of the system of interest. And please remember that for this system of interest, I cannot say that it's isolated, or I cannot use any of those assumptions. Its phase space is not uniformly occupied with phase space points. Definitely not. They are uniformly occupied for the phase space of the entire system, this plus that, but not for this small subsystem, because for this one this energy is not a constant of motion, it is changing. Maybe it is peaked around one particular value, but still if it is peaked around a value, that does not tell me that the other microstates I should discard. And I will show you that indeed if the volume and the number is much smaller, the peak is it may be described by a Gaussian, but that is secondary. The first thing is to realize that all microstates of this system are not equally likely, because it is not an isolated system. I cannot apply postulate of equal a priori probability for this system of interest. I need to let me see, where is it? Maybe this one. Yes. I just want to see this. So, okay. So this is the phase space of my system of interest, and I want to know the phase space density, the density of points here. Okay. So in particular, since this refers to system 1, so here is a bit of confusion that may arise. So I'll write, I don't know, probably row 1 is okay. Okay, let me write it row 1. Row 1 of Q. So please remember that Q refers to the generalized coordinates of my system of interest, and P refers to the generalized momenta of my system of interest. This set doesn't include the generalized coordinates and the generalized momenta of the rest of the external world, because I chose to find out what's happening in the phase space of this small system of interest. I may be interested in finding out what's happening in the entire subspace, entire phase space, but let's say I want to know what is the density at this point, what's the phase space density at QP, where QP corresponds to a point here. So this is my QP. So in some books they write it as a row of Q1 P1, where the subscripts refer to system 1, and you have to include all the coordinates and all the momenta of system 1, because that's what I am interested in. So how do I do that? So okay, let me just see. So this will be proportional to so let's look at it this way. So what I want to know is what is the density at point QP of system 1. Once I am given QP and I know what the Hamiltonian of my system 1 is, I can associate an energy to this microstate, right? Let's say that energy is E1. I did not say that E1 is a constant of motion, E1 is this and that, whatever, nothing. Let's say that energy is E1. So then this should be, let's see if this is obvious, or let me also do it this way. So what I have to do is, or let me do it this way. It's a question of notation. Yes, maybe I write it like 2 here, but that looks like a square. Let me see. I don't know which is a good way to do. So let me see. I want to know how many times do I get a point of a microstate at a particular point in this phase space for system 1. Corresponding to this one microstate in the phase space of system 1, there would be many microstates possible for system 2, right? And I have to count all of them, subject to the constraint that for this microstate of my interest, for which the energy is E1, I have to consider all microstates which are possible in system 2, for all of which the energy is such that the sum of energies is a constant, right? Because the two, they together make up a composite system. So what I do is that I ask you a question. Okay, at point Q1 P1, 1 refers to system 1, my system of interest. What is the probability? So how many times do I get a point at a particular location, or what is the probability that I get a point here? What is the probability that I have a microstate here? That means I have to take count of. So the way to make this counting is the following. What is the probability that I have a point here? To put it differently, given that I have a point here, what are the all possible values possible, what are all values possible for the phase space coordinates of system 2, subject to the constraint that now that I have told you what's the microstate of system 1 is, it has some energy E1. So, all microstates of system 2, they all need to be taken into account subject to the constraint that the energy of all those microstates plus the microstate of system 1 has got a given value. And this, see, this is I am integrating over all phase space coordinates of system 2 subject to the constraint that the energy of all those microstates lies in the range E minus E1 and E minus E1 plus delta, where what is E1? E1 is the energy of my microstate of interest. So, that is just gamma 2. So, that is what I was writing in the first place. So, this is just proportional to gamma 2. You remember this is the phase space coordinates for system 2. So, this is by definition gamma 2 of E minus E1. You see here, same setting that I had used earlier, I am using the same setting. I have changed my question. I was asking initially, here is my composite system, how many phase space points are, what is the available phase space volume for the entire system? That is equal to gamma 1 E1 gamma 2 of E minus E1 sum over all possible values of E1. Now, I am saying, I am asking a different question. I am asking, forget about the phase space volume of the entire system. I am simply not interested in that. I am just interested in finding out what is the chance that I have a phase space point, some phase space density at a point in the phase space of only system 1. And since system 1 is connected to system 2, therefore, given that I have a microstate here at for system 1, there are many microstates which are possible for system 2. And I have to take care of all of them, provided the energy of all those microstates plus my energy of the energy of the point where I am standing, my observation point, is equal to a constant. Okay? Yeah, so of course E1 is not fixed. So, but I am saying what is the probability that I get a point at a particular value Q1 P1. So, Q1 P1 is related to E1, and of course, if I change my observation point, E1 will change, everything will change. Yes, at a fixed Q1 P1. These are variables. I am standing somewhere here. I am asking how many microstates are possible. It's like, think of it this way, that you have a, I don't know, two coin toss, let's say, and you ask, in the two coin toss are somehow, let's say, coupled or something. So, you are asking what is the probability that I get a head with the first coin. So, corresponding to getting head with the first coin, there are many possibilities available for the second coin. The second coin could be head, the second coin could be tail, and so on. So, I have to take care of all of it. So, is this clear? Somehow I must say that in most books, I mean, people, at least students, get confused as to I am using the same setting, but suddenly instead of getting gamma 1, gamma 2, I have just gamma 2. Well, what happened to gamma 1? Gamma 1 is there, but I have changed my question. I have kept the setup, I have changed my question. I have changed my question for the very simple reason that for a realistic setting, you will never have the access of, you will never have access to what is happening in the rest of the system. That is the idealized situation, where maybe you bring a chalk and a, I don't know, cheese maybe. That is a strange combination, but just so maybe I bring these two pieces of chalks together, and okay, this is a comparable size, and therefore I am asking for the probability distribution, the distribution of phase space points in the phase space of the composite system. That is that. But now my system of interest is this chalk, and the rest is the, like everything external to it. So, that is that. And typically I can draw the phase space or like visualize the phase space of the chalk, but for the rest of the world it will be like very large, and I just do not need it for any practical purpose, because ultimately, why I do not need it? Because ultimately I will make measurements only on the chalk. So, whenever I see, we have defined, we have said how to make connection between this picture of phase space coordinates and some measurable quantity. So what you do is that you take your measurable quantity, you measure it for a given microstate, you average. And typically I make measurement with only the chalk. So let's focus only on the phase space of the chalk, forget about the rest. They are there, they will appear, they do appear, and the way it appears is that the way they appear is that, you know, this is the phase space volume for system 2. But once I have it in this form, what I can do is that I can do Taylor expansion, because I know that E refers to the entire system and E1 refers to the system of interest, and E is much larger than E1. So if you do that, and I will skip the details, I mean it's just a very straightforward Taylor expansion and so on. So what you would get, I mean the final expression that you would get is the following, or maybe it is probably worthwhile to do this little algebra. It's a simple algebra, not much profound. K log, so let's look at this guy, K E minus E1. Achha, before I do that, it should be very clear in your mind that given a microstate in phase space 1, I can at once associate a value of energy to that microstate, because I know the Hamiltonian of system 1. To find the energy of a given microstate in system 1, I do not have to invoke system 2. Only for the composite system, if I am interested in the energy of the composite system, do I have to take care of the contribution from system 2. Just for system 1, well, by definition I do not have to worry about system 2. So when I say P1 Q1, there is a value of energy associated to it, which is E1, and that actually is here. And as I move this point around, as I change the values of Q1 and P1, E1 value will change, E will remain constant. Okay. So then, let's look at this guy. Instead of doing a Taylor expansion of this one, you will see why I do a Taylor expansion of this one. So this is by definition, see, this is 2 refers to system 2. That is the phase space volume of system 2. So by definition, K log gamma 2 E minus E1 is S of which system? 2, right? Because this is the phase space volume of system. This is an argument. The argument may depend on system 1. The function itself is of system 2. So this is by definition S2 of E minus E1. And then I know that E1 is much smaller than E. So what I can do is I can do a Taylor expansion, and if I do this, the leading term will be S2 of E minus E1 del S2 of E2 by del E2 evaluated at E2 equal to E, right? This is just Taylor expansion. This has to be evaluated at the point like around which you are doing the expansion. But then this one, del S2 E2 by del E2 equal to E, this is by definition the temperature, right? This is the temperature of system 2, right? Because by definition 1 by T is del S2 of E2 by del E2. So this is the temperature of system 2, but we know that it is also the temperature of system 1, because the two systems are in thermal equilibrium. So is it not better to write E minus E1 rather than E2? Yeah, because here you can write anything. It's a dummy variable. I have to derive with respect to something and then like evaluate it at E. Right? You can write it like I don't have to like even write E2. You can write it Y. Doesn't matter, because anyways I have to evaluate it at E2 equal to E, Y equal to E. No. People write E2 because that's the natural. I don't know. You can write whatever you. I should not write E2 E minus E1 because I am doing Taylor expansion. So when I am doing Taylor, see f of x plus delta is f of x plus delta f prime x. So that is what I am doing. Delta happens to be minus E1, so that is it basically. So this part is clear, right, that this is the temperature of system 2 by definition, and I know that the temperature of system 2 is equal to the temperature of system 1. So I do not have to put a T1 here or a T2 there. I know that T1 is equal to T2 because you see when I am doing this, the system is still in thermal equilibrium. The system is in thermal equilibrium, the two temperatures are the same. I am asking something about system 1. Is this clear that the temperature has to be the same? So I do not have to put T1 or T2 there. I can put, but then eventually it will come out to be, I mean, I know that the system is in thermal equilibrium. So I hope this transition is clear. I mean, it's the same setup that I had for the microcanonical thing, excepting that now I am considering the case where one system is much smaller than the other one. That's it. And I am doing some Taylor expansion, and I have changed my point of view. Initially, I was asking for the phase space of the entire system what is happening. Now, I am asking what is happening in the phase space of just this small bit, small system. Okay, so with that, so I know what is k log of gamma 2 of E. So then if I just invert it, so what I do is that I divide by k, and then gamma 2 is exponential of this thing. So I will, using that one, say gamma 2 of E minus E1, that is exponential of S2 of E by k of exponential of minus E1 by kt. I think I do not need it anymore. And this we already said, this is just proportional to gamma 2 of E minus E1. This is clear, right? What I did was I just took this expression and exponentiated it, and I just plug this in here. So what I get is this is proportional to e to the power S2 E by kt times e to the power minus E1 by kt. Huh? The first term will not contain any T. The first term is going to, I'll drop it soon, I mean, I'll tell you why, but, so this is okay, right? I mean, one way to check if you have, okay, so let me, but it should be okay, right? That I am asking what is the probability that I get a microstate here at point Q1, P1, and that has energy E1. So that is indeed proportional to some factor of E1 divided by temperature. Temperature of which system? Well, temperature of either system, because the two systems have come to equilibrium. Now what I can do is that, see, there is a proportionality factor. This proportionality factor is just to normalize it. Okay. What I can do is that as far as this thing is concerned, Q1, P1, I can consider this to be a constant. Why? Because this is a function of E and k, S2 of E, but E is a given number. This will be some number. This is not a function of the phase space coordinates of system 1, right? This is not a function. It is a number, whatever it is. I am not throwing it away. I am just saying that it does not depend on the Q1, P1. So therefore, I can write a rho of Q1, P1 is equal to, and I'll tell you why do I write it. E of, but what is my E1? E1 is by definition H of Q1 P1. That's the Hamiltonian corresponding to this microstate, by KT. Divided by, see, whatever piece I have, I can absorb it into defining my normalization. Divided by dq1 dp1 e to the power minus h of q1 P1 by KT. That's a normalization by definition. I just take this guy, I have to integrate over the phase space coordinates of only system 1. Whatever is there, I am not throwing it away, I am just saying that I can absorb it into defining my normalization. So what this thing is telling me something very interesting, that in the phase space of the system 1 alone, the points are not going to be uniformly distributed. That is what I had expected anyways. It is telling me the points are not going to be uniformly distributed. If you ask me, if you give me a microstate Q1 P1, what's the probability? Well, what I will do is that you say, okay, give me your Q1 P1 values, I will put them into the expression for the Hamiltonian of system 1, I will get a number, I will exponentiate it, put in this factor of KT, and this is what is the probability of that given microstate of system 1. Is this okay? So let me repeat, like this part is not well explained in most books, or perhaps it is well explained, but it is difficult to, you have to think about it. I mean, it's the setup, the question has changed, and because the question has changed, you can use the same tools, but then you have to look at it from the right point of view. This temperature is fine, temperature of which system? Either one, doesn't matter. Like anyways, the temperature is the same. Well, the temperature is defined the way I have defined it, is the derivative of the S2 function of the second system with respect to first, but that is also the temperature of the first system. And now I will show you that with this treatment, I will show you that indeed, if I ask for the energy distribution of this small system, it is peaked around one value. There is a small width around it, and this is consistent with what I have been telling previously. I was telling you that there is one value E1 bar. Most of the microstates are concentrated around that. This should show up now here, because now I am asking microstate by microstate. What is the probability of this one? What is the probability? It better shows up here, and it will show up. So I think I had written some. Sure.
When we are talking about the question with the a priori, that was when I was talking about two systems on
Closed system. When I am talking about the phase space of a closed system.
And the equilibrium condition.
Equilibrium.
Will lead to that.
Absolutely. Different question. Exactly. It's quite natural that if part of it, exactly. For the entire system, for the whole world is isolated. So this postulate of equal a priori probability is applicable. Just recall, what we have been doing in the lectures on conservative systems. We were always dealing with a Hamiltonian system. We had said that the volume is preserved, and yet this volume gets, it develops these tentacles and so on, so that the system becomes ergodic, and therefore you can replace a time average by a spatial average. And I don't know, in presence of complete ignorance, what I will do is that I will assign equal probability to each and every microstate, but that is all in the setting of a system for which energy is constant. Here for this part energy is not constant, for this part the energy is not constant, but for the entire one it is constant. So if my focus is on the phase space of the entire system, then everything works out. But if my focus is the small component of it, this small component is needed just to do this Taylor expansion. If you don't do this small component approximation, well, you will get a row of Q1 P1 to be proportional to gamma 2 of E minus E1. That's it. Huh?
It's not explicitly highlighted in books.
Yeah, I don't know why, but I don't know why it is not. I mean, yeah, I have no idea why it is not there. So Musansi, you know why this thing is not explained this way, that this it's the same setting and so on, but you are looking now at the phase space of the system 1, because somehow it looks like you have two systems in contact and suddenly you have this I mean there is kind of a jump in the way things are presented, but perhaps it is obvious or not obvious, I don't know what it is. So I want to just show you the energy distribution of the okay, so before I do that, let me define a very important. You see, typically it is the general thing that, you know, whenever you have a distribution and you have a normalization factor, you take the log of it and it's going to give you something important. So if you remember for the microcanonical ensemble, you had the accessible phase space, this gamma, you took the log, you got entropy. It should be possible now, or it's not a question of something being possible, but it is very well likely that now if you take the log of the partition, the normalization factor, it would give you something interesting. It may give you, I mean there is a good chance that it will give you. So let me just write out this thing. So this is e to the minus beta h. Well, now that I know that my system of interest is 1, I do not have to keep writing 1, 1, 1, 1. I can just drop q 1 here, subscripts, with the understanding that now what I am interested in is the phase space density in my system of interest, and the density is given by this. So this, I mean, on the face of it, it might look like what is happening. I mean, here is Q and P, but you have to remember that what I am asking is, what is the phase space density at point QP, and the way it is determined is through the Hamilton function, through the Hamiltonian. I don't know, like it's quite, it could have been in some other way, but well, that's what it happens, that it is determined through the Hamiltonian. It could have been in some other way, like maybe it is e to the minus beta q square a to the minus beta p cube or something, but that's the right combination that you have to consider is the one that is dictated by the Hamiltonian of the system. But that is what it is, because we are considering energy fluctuations anyways. So this thing, this normalization constant that you have here, that's called the partition function. By the way, such an ensemble, so before coming to normalization, so this will give you a collection of microstates with a certain distribution, okay, certain number, okay. This particular microstate is going to appear that many fraction of times, you know, if I do experiment or something. So such an ensemble is called a canonical ensemble, because here the phase space in my system of interest, the phase space is not uniformly filled up with the phase space points. They are filled up in a particular way, namely you take a q and p, you evaluate the h function, and e to the minus beta h is going to give you the probability. So this is canonical ensemble, and this thing, this is the normalization factor. So this is what is known as the canonical partition function. Let me use the notation used in Carson Wong, but in like other books they write Z and so on. So before so can somebody tell me what are the independent variables? What are the variables that are, it's not E, because for system 1, the energy can have many different values. So E is not the one that I can control. What I can control? I can control the temperature, because what I can do is that I can choose this system of the temperature of this system of interest, whatever I like, and I am sure that if these two systems are brought in contact with each other, this guy, this big system is going to dictate what's the temperature of this system going to be, because the systems will be in thermal equilibrium. So T is one variable, and I did not do anything with V, I did not do anything with N, so this is it. So in the microcanonical ensemble, my independent variables were N, V and E. So if you remember, microcanonical was N, V, E, and canonical was N, V, but E is not a constant of motion, many different values, but T. The transition to grand canonical, I mean, it becomes almost trivial at this point, but before I go to that or talk about this energy distribution, let's look at what's log of QNVT going to give me. So I don't know, for some reason Carson-Wang uses this letter A. Like, is it standard? Instead of F. So what I do is that I do minus KT log of QNVT, and I claim that this gives me some quantity called, so let me just stick to the notation of Carson-Wang. I claim that it gives me some quantity which is called the Helmholtz free energy. So we did not discuss this while discussing thermodynamics, so I'll do it now. I'll show what's the importance of this Helmholtz free energy. But for the moment, you just remember that you take the log and then you multiply by KT, and like again that same thing comes in, that well, this may have some dimension and so on. So in Carson-Wang or like any book, what they do is that they'll have a factor of h to the power 3n, and also this n factorial is sometimes put in by hand because they say the particles are indistinguishable and so on. But up to that thing, so this is so let's look at what this guy, what is it about, what is this free energy about. So for that, one has to go back to Clausius inequality and show how and see how does free energy, what is the importance of free energy. Let me just again stick to my notes. Is it somewhere here? Maybe this one. Okay. So this is Gibbs potential. Okay. And I'll also tell you something about some recent development in this. So shall I rub out this? This is clear, right? Small, big, etc. So during the lunch break, I got a lot of questions like, what is this microstate? Can I measure it? What is its utility? Can I go and find it? I mean, it's good to ask those questions. I mean, don't think too deeply about microstates. I mean, okay, once you have understood that, I mean, you have to get to a point where you have a quantity that can be measured in experiment. So that will show that what you have been thinking about is right. So it's I mean, in principle they can be measured, but in practice not. I mean, not really measured, but they can be counted or something.
Actually, that thought process will be running till we understand that.
Sorry?
That thought process about the microstate will be running till we understand.
Yeah, sure.
And then it will stop.
Yeah. No, so let it be there, but acha, this one. Okay, this one. So let's look at this Clausius inequality. So what it told me was the following, not really Clausius inequality, but a corollary of the Clausius inequality. It told me was the following. So if D cross Q is the amount of heat absorbed by system in going from A to B, so D cross Q by T is less than equal to SB minus SA. It's going to be an equality if I go from A to B along a reversible path, like otherwise it's going to be an inequality. And suppose I go from A to B along a path for which the temperature is constant all through. Suppose, and it's a particular transformation that I can think of. So then I can pull out this factor of T because it's constant, and I can bring this here, and then I'll have an integral A to B of D cross Q. That's the net heat absorbed by the system. Okay, so what I will have is delta Q, that is the total heat absorbed by the system, that's less than equal to T delta S, where delta S is SB minus SA, the change in entropy in going from B to A. But I know how to write delta Q in terms of delta U and delta W, because I know the first law of thermodynamics. So that tells me the total heat that the system absorbs, part of it goes into increasing its internal energy, and part of it goes into doing useful work, some work by the system. So I just plug that in there, and what I would get is that so delta U plus delta W, so what I would get is that delta W is less than equal to minus delta U plus T delta S. I just use this one there. And now if I define, so you see that the work done by the system can only be smaller or equal to some quantity, something that we don't yet know. It is defined in terms of U and S. Some quantity for which the independent variables are U and S. Okay. So let me define a quantity A to be, I just call this the whole of the right hand side. So the first thing to note is that it's a state function, because U is a state function, S is a state function. T doesn't depend on the state anyway, so this whole thing is a state function, so I should be able to define a state function. It has to be a state function. So I define a quantity A which is U minus Ts. Suppose I do that. So then you can check that delta U is equal to delta U minus T delta S. Why there is no minus S delta T? Sorry, I'm sorry. Why there is no minus S delta T? Temperature is constant for this particular process. So this is less than equal to delta U, so minus delta A. Yes. And if it so happens that you are dealing with a system in which you are dealing with a system for which, the system is in mechanical isolation. Mechanical isolation means what? We have already talked about it. It's like energy may change, but it cannot do any work. Let's say fixed walls. That's what we were considering anyways for the system of interest. That its energy may change, but the partitioning between the system and the external world is not allowed to move, and therefore the system cannot do any work. That's a definition of work, that something has to move, something on which the system is exerting some force. If this thing doesn't move, then there will be no work done, and therefore delta W will be equal to 0, and so what this thing tells me is that it gives me an important result, which is that would tell me that 0 is less than equal to delta A, or delta A is negative. So the statement is that for a mechanically isolated system kept in constant temperature, mechanically isolated. Why mechanically isolated? Because I am considering the situation where the system cannot do any work. Therefore, it is in mechanical isolation. For a mechanically isolated system at constant temperature, it can do whatever it likes, but still this A quantity, it doesn't ever increase. This I have, it becomes negative or 0. The change becomes negative or 0. If I start with some state A and I go to some state B, it cannot be that the free energy of, so this A quantity for state B is larger than that of state A. It's either the same or has gone down. And therefore, what will be the state of equilibrium if I am doing a change? It will be the one in which the free energy has got its minimum value. And this A is what is appearing here, the same A. What about the, what about the variables here? Did I say that it is a function of t and s? But now I am saying it is a function of v and t. What's going on? Yes, exactly. So you can use that and get this as the dependence. These are the natural variables for the independent variables for the canonical ensemble. So you see that this gives you a very important result. I mean, it is kind of generalization of the fact that, let's think of it this way, that we had learnt in classical mechanics, if there is a particle moving in a potential, that somehow I have to minimize the potential to find the equilibrium point. There is a particle which is so there is some potential. Now if I let go, let the particle do whatever it likes, then it is going to go to the minimum of the potential. It's generalization of that fact. It will go to the minimum of not the potential, but of the Helmholtz free energy. Because you see this U, it contains, so where is the definition of U? A, there is a piece which is coming from the potential energy, this is. But you have to also remember that there is entropy. At a finite temperature, there is also entropy, because the moment a particle goes to the minimum of the potential, the number of microstates will change. Like initially the particle is going to move around, so many more microstates are possible. And if it so happens that the particle goes and sits at one point, the number of microstates change, number changes, that I have to take into account. So in microcanonical ensemble, can someone tell me what is the quantity that I should maximize or minimize to get the equilibrium? No, not energy, entropy. Isolated system, we have seen, no, from the Clausius inequality when I did, see d cross q by t, it's just the fact that d cross q by t, remember this form of the Clausius inequality, is b minus sa, but the system is thermally isolated in canonical equilibrium, so this part is 0. If this part is 0, what this thing tells me is that SB is greater than equal to SA. So the entropy will only increase. I mean, the equilibrium state will be the one in which the entropy is maximized. In microcanonical, in canonical, it will be the Helmholtz free energy which has to be minimized, because you see, if you increase entropy, this is negative of that. It's kind of like that. In entropy, maximization of entropy is like minimization of free energy, kind of, not really, but sure.
Free energy, in the sense that delta W is the work you can extract. You might think you can change all the internal energy to work. You can't.
Yeah, okay. So
you can change only part of it.
you
that is free.
exactly. And why you don't, why you lose some of the, so it's like I do some work on the system, why all of it doesn't go into, you know, this is doing some work on it, I am losing, so that this wooden thing is gaining. I am doing some work. If the transformation is reversible, then whatever I do on the system, this is all of it goes into increasing this thing. But if it is irreversible, because irreversible means that there are dissipation and friction and so on, and therefore all the energy that goes into the system, right? I mean, part of it just disappears. I cannot get it back. I mean,
That is the inequality.
that's inequality. Oh, acha, equality.
I'm saying you can't extract delta U.
Okay. Yeah. Okay. You are saying here. Okay, I see.
So TS part of delta U cannot be taken.
It cannot be taken. I think this is what Devraj was mentioning, that, you know, this entropy is what you kind of lose. There is this thing that is there. Turns out that so this is the work done by the system is less than equal to minus delta A. So I can just put a sign minus sign here. So that it becomes work done on the system and increase of the free energy. I can just, so I can write it like this is the work done on the system. So that's greater than equal to delta A. So whatever work I do on the system, part of it goes into increasing the free energy, but part of it gets lost if it's a irreversible transformation. And it's a remarkable fact that if this is this, but if you just exponentiate it, if you just do e to the power minus beta delta W and then take its average, like average over the canonical measure. Well, not quite canonical measure. So no, let me not get into that because it will make it. So there is an equality that comes out of it, which is called Jarzynski's equality, but let me not get into that. Maybe we can discuss it during tutorial, because I want to really show that this energy distribution is. By the way, one thing I don't talk about Jarzynski's equality, but so to say, but then let me just mention one thing, that the whole of thermodynamics, the way we have set it up, we have said that we are going to deal with a macroscopic system. So this delta W and delta Q and so on, they all refer to the macroscopic system. But you may as well deal with a microscopic system. A very good microscopic system could be a DNA for which you try to pull and then you do some work on the system and its internal energy. Because my definition of macroscopic system is not necessarily very big. What I said is that it has to involve a large number of interacting, and DNA has got a large number of interacting degrees of freedom. It doesn't have a macroscopic in terms of length and so on. So it turns out that for such a system, all the thermodynamics have to be in all of the equations that I have written down. I mean, this is, you need, if you don't understand it, you don't have to, but this is just for those who are interested. All the thermodynamic laws have to be interpreted in terms of averages. On the average, because work done for a very small system like DNA and so on, it will show huge fluctuations. So what has been established in recent years is that all of these laws in this entropy, energy, etc., they are to be interpreted in the sense of averages. You may have huge fluctuations, and those fluctuations may violate these inequalities and equalities and so on. So this field is known as stochastic thermodynamics. I mean, now it's very much in use, and I think the chemists are the ones, they use them for making important predictions about chemical reactions. Now,
minimization of Helmholtz energy is a kind of optimization increase in the entropy.
Yes, exactly. Yes, exactly. That I want to, Absolutely. Because these two are competing. You want to minimize the energy, you want to maximize the entropy, so kind of balance. And if T is 0, then you see that minimization of energy is same as minimization of Helmholtz free energy. Before I go to the last bit about this like energy thing, since this is the last class and we'll have one tutorial on Monday, but you see here till now what I have done, I started out with this system that is allowed to exchange only energy, isolated system, and then I went to the canonical ensemble where I am interested in this subpart that is allowed to exchange energy with the rest, and I am interested in the phase space distribution of this system of interest. Still the number of particles was a constant, it did not. You can generalize it to the situation where this small part is exchanging energy as well as particles. So then what I would do is that this small part plus the big part, I may consider the whole as a canonical ensemble, because for the whole thing the number is not fluctuating, and I know what is the phase space distribution for the whole thing. Now what I do is that, it's the game is, you know what you have to do. That let me just do it before I go to this, because this jump from okay, now let me do this and say a few words about equivalence of ensemble before I go to this like energy fluctuation. So now you consider the situation where there is this small part and there is this big part, and this whole thing is in contact with a bigger part. So this thing is now in canonical equilibrium with the rest, and you are interested in this small part, which is of course exchanging energy as well as number for this one, and the whole thing is now canonical ensemble, and I am interested in the phase space distribution of this part, let us say. So what I have to do is the following, that I would look at this one, this now refers to the full system. I have to integrate out over all the degrees of freedom of this one, with the constraint that the number of particles here plus here is a constant. And if you do that, you will get grand canonical ensemble. It's just straightforward. It's just maybe you will talk about marginals and no, okay. So this is kind of like marginal distribution. That you have a distribution for a large number of variables. You say that I'm not interested in what is happening for a set of those variables. So I integrate those out. I will be left with some, and that will give me a distribution of those some variables. And in grand canonical ensemble, the partition function is the grand canonical partition function. If you take the log, I promised it should give you something interesting. It does give you something interesting, which is the pressure. PV is equal to KT log of the grand canonical partition function. And now grand canonical system is one in which the energy is fluctuating, the number is fluctuating, everything is fluctuating. Well, the volume is not fluctuating. You can construct a partition, a grand canonical ensemble for which even the volume is also fluctuating. Now a word about how do I go from one ensemble to another to another. You see this yeah, this energy is yeah, there. So the whole thing is a the whole thing is a canonical. It is exchanging with energy with the other, but the whole thing is canonical, means the whole thing is at a given temperature T. Why I am interested. Okay, look at it this way. And I'll give you a physical. You can look at it this way. Maybe my drawing was. You have this system which is in contact with the external world, and this is exchanging energy, but not particles. So it is in microcanonical ensemble. For such a system, I look at a small subsystem of it, and this is exchanging energy and particles. So for this one, it is not a microcanonical ensemble. It is not a canonical ensemble. It's part of a canonical ensemble. That's why. Why it will not? Because why it will not? Because it's just a part of the system. So I'm looking at some degrees of freedom. No, if the particles. Yes, exactly. Okay. Or like think of it this way, that the particles can go back and forth, and that will lead to some exchange of energy. Now I have relaxed all those restrictions that were there in defining microcanonical. You look at only those for which the energy is constant. So this is not there. Now, a word on how do I go from one ensemble to another. So, this point is a bit tricky or maybe not so tricky. So, it is the following. So, in the microcanonical ensemble, the energy is constant. The natural variables are energy. In the canonical ensemble, it is the temperature which is constant. I mean, it is not constant of motion per se, but it is constant. If I somehow can show that in the canonical ensemble, for the system of my interest, the energy shows fluctuations, but are peaked around a particular energy value determined by the temperature. Then what I can do is that, suppose somebody gives me a microcanonical, so this is microcanonical at energy E, and somebody gives me a canonical system, so this is my canonical ensemble at some temperature T. And if I am able to show that for this one, for this system of interest for which there are energy fluctuations, if I can somehow show that this energy distribution is peaked around a particular value E1 bar, that is function of T in this way, and moreover this peak becomes really more like it becomes sharper and sharper as the number of particles increases here. So, what I can do is that I can choose my temperature in such a way that the mean energy here becomes the actual energy of the microcanonical ensemble. Is this point clear? I have not shown you, I am going to show you, that is the last part that I am going to do. Well, you kind of understand that it has to peak because of the proof that I had done. I had said that most of the microstates for this one is going to be around a value E1 bar. So, this is that E1 bar, and I know that E1 bar is a function of the temperature. Why? Because I had that equality, no? If you remember, del S1 E1 del E1 at E1 bar is equal to, you remember that equality that I had, del S1 E1 del E1 at E1 bar is equal to del S2 E2 del E2 at E2 bar, and this was what we had defined it to be the temperature. So, what I can do is that I can choose the right heat bath, the heat bath which has the right temperature, which will ensure that for the system of interest most microstates have energy E1 bar such that this E1 bar is equal to E, then I am done. Whatever I get here, I am going to get the same thing there. Similarly, to go from grand canonical to canonical ensemble, it will not be the temperature which will be the same, it will be the chemical potential which will be the same. So, what I have to do is that I have to somehow show that number will fluctuate for grand canonical, yet there is a chemical potential that allows me to get small fluctuations around a value of mean number, and then I tune my chemical potential such that the mean number becomes equal to the actual n value of the canonical. Then I have established that grand canonical is equal to canonical is equal to. There are caveats for long range interaction system, most of the things do not work, but to do that one has to, it is not, I will need not one but two lectures. Let me just show this result, that this indeed as n increases for this system of interest, the energy distribution is peaked around a value, and the peak the distribution becomes more and more peaked as I increase the number of particles. It is a Gaussian actually, it is Gaussian close to the mean. Well, there may be for the tails one doesn't really know, because it is a Gaussian, then I do not have to worry about the tails. So, I hit it, it is actually very simple, so I do not have to even no, but first, okay, before I do, let me take 5 more minutes, but it is important that you understand this equivalence of ensemble. Why this equivalence is important? Because you see in the microcanonical ensemble you had many more restrictions, that you restrict to those microstates for which the number is n, the volume is V and the energy is E. Typically you do not have such, like you would like to get rid of those restrictions for practical reasons, that you do not have a way to tune the energy of a system. What I have is, I have a way to tune the temperature of the external atmosphere. Like, let's say you have a system in contact with a heat bath, let's say an oven or something that you put in. There is no way to tune the energy of the system. Bread, burger that you are going to eat tomorrow for lunch, and that is what I am told. So, the burger temperature I cannot tune, but what I can do is that I can tune the temperature of the oven, and if the system comes to thermal equilibrium, then I am sure there is a temperature of the burger. So, I do not have a way to tune the energy, but I can tune the temperature. Similarly, I do not have a way to tune the number of particles. I mean, the number is, if I am given a sample, it is what it is. I mean, so, but what I can do is that, this gives a way to relax constraints which were there in microcanonical ensemble. And you may define like any ensemble of your interest, like maybe in the tutorial, in the tutorial, what I will do is, typically there is a lot of confusion about how to go from this PVT system to a magnetic system. I mean, you do not know whether it is HM, or some people say MDH and then HDM, so you maybe toss a coin or something. So I will show you that you do not need to toss a coin, it is actually just one. And so let me do this last bit. I do not know which is a good place to read about equivalence of ensemble. Somehow it is not there in, maybe this cuts. Wong has
a small paragraph, but it's
acha.
emphasized much more, but it's there.
Acha, it's there. So this side I forgot somehow. Okay. Okay. No, you are saying something about some paper by like Uhlenbeck. That's in this Nelson Wax's? No, not there. This collection by Nelson Wax? No, not there. Achha.
That was in a series of books called Studies in Statistical Mechanics, edited by E.G.D. Cohen.
Oh, acha. Fundamental problems? No.
Fundamental.
Fundamental problems in statistical physics. Acha.
Probably 1940s.
Acha. Sorry? Yeah, this equivalence of, okay. So, this I should mention that this equivalence is valid only in the thermodynamic limit. Only in the thermodynamic limit will you have very fluctuations which is very, narrow. Exactly. I'll show that in fact the relative energy fluctuation goes as 1 by square root of n, where n is the number of particles, and similarly for the number fluctuation also you can show a similar thing. This calculation is there in Wong, but I'll just show you the physics part of it. I will not do the. And by the way, in the microcanonical ensemble, what's my definition of internal energy that Vaibhav was mentioning? In the microcanonical ensemble, indeed the internal energy is the average of H over this microcanonical measure rho, because now energy is fluctuating. Okay, so this part. So let's look at the definition of the canonical partition function. So it is Qn of V of t. Okay. So this we said it is by definition dq dp. I think there are more than one ways of doing it, but this is one possible. So this is e to the minus beta h pq. This is qp. Right. So this is by definition. Now this I can write it as, what I can do is that I can introduce a variable e, and then what I can do is I can write it trivially as e to the power minus beta h of qp, and then what I have to do here? The students, you have delta h of qp. Because if I integrate over here, this is, but I know this property of this very interesting property of delta function, that f of a del of a minus b is equal to f of b delta a minus b. Doesn't matter which one you take, right? So what I can do is that I can now, because it's multiplied by a delta function, I can replace h by e and pull that out of the integral. So if I do that, what I would get is dE e to the minus beta e, and then dq dp delta of e minus h qp. But this thing you have seen already. This is what? This is the gamma e, the definition. I am just gamma e or sigma e. This is the microcanonical measure, the microcanonical volume of accessible phase space, right? So then I know what it is in terms of the entropy. S was equal to k log gamma e, then gamma is equal to e to the power s by k. So let me just do that here. Since I write, so so this quantity now I can do. So this is what, e to the power s by k, or I can write it as Ts, and this, I guess this is okay, right? S by k, right? Beta is 1 over kt. Maybe I haven't written it ever, like I did not write it. Beta is 1 over kt. Now let us look at this. How many of you have done a method of steepest descent and saddle point approximation or something? You must have. Okay, so let's look at this thing. See, S is a function that's proportional to n, that's going to increase with n. And E, remember we are dealing with short range system. E is linear in n. So there is a factor of n here and there is a factor of n there. So what do you expect? You have some integral, you must have done this somewhere, dx of e to the power minus n fx. What happens if n becomes larger and larger? How do I evaluate this integral? So what I have to do is that I have to take the function at which take the value of x at which this function is minimum, right? And so this will be e to the minus n f of x star, where x star is the value of x at which fx is minimized. And this unfortunately I don't have this thing, but n doesn't really have to be very large. I mean because it's an exponential, so n doesn't have to be really 10 to the power 23. I mean 15 or 20 will do it. It will really make it very sharp. Sharper than the one that Mustansi was drawing. I mean the 6000 and so on. Just a property of exponential. So let's do the same thing here. What I'll do is that I'll choose, see this is an integral over E. So when you write these equations, you have to remember what's the variable. T and S is a function of E. But so I have to choose the value of E at which this is maximized. So that will satisfy, obviously 1 is equal to T times del S del E, and let's call that value E star, right? So what I did was I have to minimize this function. So if I take the derivative of this with respect to E, I get 1, and this is T is not a function of E, and I get this. Rewrite it, you recover what you should, it was there, no? 1 by T was indeed equal to del S del E. So at E star, and if you, what you can do is that I just took the first term, but you can do a Taylor expansion about x star. The first term will be 0. So if you expand fx like about x star, what do you get? You get fx is equal to fx star plus f prime x star times something, but f prime x star is 0 by definition. So the first leading order term is x minus x star whole square, right, the quadratic term, times f double prime x star and so on. So if you plug that in here, then what will be this integral? This integral will be what that it becomes a Gaussian. Gaussian peaked at the right value. So this P of E, it is Gaussian which is peaked at the value E star, and what is the value of E star? It is the value at which del S del E star is equal to 1 over T. This is the right value. I had told from the beginning that most of the microstates are going to have this particular value of energy such that del S del E is equal to 1 over T, the temperature of the and you can do the same thing, you can do this calculation. It's there in Kurzanwa. It tells you how do the relative fluctuation, the variance depend on n, and you can show that this delta star E by E star, this is the width sigma that Mustansi was mentioning, divided by E star, it is proportional to 1 by square root of n. It's actually trivial, because when you expand it, you will get E minus E star whole square divided by sigma square. So sigma with the factor of n, n comes from this E and S.
It's worth pointing out that, as you correctly emphasized, ds by dE evaluated in E star is
1 over
the temperature as evaluated in the microcanonical.
Yes, as evaluated, because okay.
So T, now that you've shown that the two are the same, E was what entered into microcanonical ensemble, S was what entered into microcanonical ensemble, T is also that temperature. So E minus Ts is the combination you got microcanonical. Now we have shown, because it's peaked, that it's equal to log of Q evaluated canonical.
Yes.
So
yes, okay, yeah.
That should be.
I think a crucial ingredient that goes into this is that you have a very big system. So this big system, the energy doesn't fluctuate so much, right? I mean, that is one thing that goes into it. Because you have a system which is in contact with a very big sea, it's a heat reservoir. Think of the chalk in contact with the rest of the world. So this big system is like a microcanonical for this one, for big system alone. So this is like as he. So it is the lesson to learn is that it is the bigger system which is fixing the value of temperature. Fixing the value of the mean energy, ensuring that the temperature of the smaller system is the same. The average number of particles of the smaller system is equal to that of the bigger system, and so on. These things are, I must say, these things are a bit subtle. So you have to, it's there. I mean, but I don't know. So this is something that I have learned over the years by just thinking about. It's not written in so clear terms in. Yeah, I don't.
Purna told us to read the book by Schrodinger.
Yeah, probably.
It's a very well-known book, but I've never read it. Very slim book. But I believe this equivalence of ensembles is there in work, but not emphasized.
Not emphasized. Or these things that it is the bigger temperature which is it is kind of what you would expect. That's why it has more. It's more powerful or dominating. I mean, it should be. That's why it's a.
Why they are dominant? Because they have more number of microstates. Because in statistical mechanics, if you have more number of microstates, you will be the
more number of microstates of the. I don't.
no, because n is large. Okay, so corresponding microstates or energy means configuration will be more.
No, but the equality of temperature, does it have anything to do with the number of microstates?